Before a silicon carbide tube enters a furnace or chemical system, the critical decisions should already be made. Temperature, atmosphere, flow media, wall thickness, straightness, and surface finish all affect whether the tube can remain stable in service. First, define the environment around the tube. Temperature, thermal cycling, atmosphere, mechanical load, and installation length. A furnace roller needs straightness under repeated heating. A protection tube needs a dense barrier around a sensor. A heat transfer tube needs fast thermal response and corrosion resistance. The same SiC body can serve different duties only when these conditions are known. When the atmosphere is uncertain, it is worth checking compatibility before the drawing is finalized. The working window starts with material behavior. The specified operating range is 1300 to 1600 degrees Celsius, depending on grade. Thermal conductivity runs from 45 to 120 watts per meter Kelvin, so heat can move through the tube rather than staying trapped in a local hotspot. Thermal expansion stays around 4.0 to 4.8 times 10 to the minus 6 per Kelvin. Flexural strength from 150 to 350 megapascals, and compressive strength from 1800 to 2200 megapascals describe what the wall and span can tolerate before deformation becomes a design risk. A closed-end protection tube is about isolation, keeping molten metal, particles, or aggressive gas away from the sensing element. A square beam is about support, holding furnace structures without losing alignment. A kiln roller is about movement through repeated heating and cooling. A heat exchanger tube is about chemistry plus heat transfer. A heating tube or radiant tube is about response time and temperature uniformity. The geometry changes because the duty changes. The grade is tied to the manufacturing route. Sintered silicon carbide is listed at 1600 degrees Celsius with density around 3.10 to 3.15 grams per cubic centimeter and porosity below 0.5%. Reaction bonded silicon carbide is listed at 1380 degrees Celsius with porosity from 8 to 17%. Silicon-infiltrated silicon carbide is also listed at 1380 degrees Celsius with porosity below 1%. So the grade defines density, pore structure, temperature margin, and corrosion exposure. Before inspection, the tube has already gone through several risk points. Forming controls wall thickness and straightness before firing starts. ADCERAX lists isostatic pressing up to 250 megapascals, with wall thickness stability within plus or minus 0.3 to 0.5 millimeters. Reaction furnaces and high-temperature sintering define density, shrinkage, and microstructure. After firing, CNC machining and end-face finishing bring grooves, threads, flange seats, and interface faces to the intended geometry. CMM measurement accuracy is listed at plus or minus 0.005 millimeters, and interface machining is listed at plus or minus 0.02 millimeters. Density monitoring, porosity checks, surface roughness review, and end-face inspection all reduce uncertainty before packing. If the tube will face corrosive liquid or high-velocity gas, density and porosity deserve special attention. The working risk begins long before a silicon carbide tube enters a furnace. Temperature, atmosphere, flow media, wall thickness, straightness, and surface finish must be defined before forming, firing, and machining. If these details are not controlled early, the real problem may only appear later under heat, corrosion, or load.